We are live. Once again, amazed by technology. Hello, YouTube. Hello, Ben. How are you?
I'm very well. How are you, sir? It's good to see you.
Good. I must be insane because I never expect it to work, and when it does, I'm surprised. And when it doesn't, that's what I expect, is to be screwed by technology. But we're
It's
working.
definitely working because I can see us on YouTube and it's nice and sharp image too. I'm saying
Good. Low latency. It started right up on YouTube
Yeah.
today.
Well, remember I finally got my AT&T fiber installed. I'm on 100 up, 100 down, which is the cheapest, but that's still fast enough for streaming, I think.
Yes. Yes. So you have some news for us, though, before we get going.
Yeah. I am now a free agent.
All right.
Yesterday was my last official day working for an employer, so
Okay.
not to elaborate too much yet because I'm still formulating my plan. But broadly speaking, I felt that life is too short. Life is too short to spend it all making lots of other people rich. It's not that I didn't, I wanted to be successful for the company, but there's other things I want to do with my life,
Right. Right. Well, you're at the age. Yeah.
I need to find a way to make good money, but have more family time. I need to, everyone wants that, and I know what actually typically happens when people start their own business or go out as an independent contractor is they typically scramble to make money and have no time for anything else. I'm planning to not do that, but to have a balanced approach. But I have some runway.
Okay.
Yeah.
So you're in the market now as an expert PCB designer and expert engineer, and we'll talk more in the upcoming shows. Yeah, embedded engineering.
Because I am actually a computer systems engineer. That was my major. I joined Altium 16 and a half years before I left there, which was a year and a half ago or more. So I joined Altium in 2004 as an FPGA guy.
Okay.
And I was a support applications engineer, and I did support the nanoboards and the FPGA workflows, and then through the course of Altium changing its spots, became a PCB expert as well. I mean, I'd always designed boards. I hand etched my own boards when I was 10 or 12 years old.
So did I. Yes.
I mean,
I ruined one time. I flipped it over and I agitated it with the copper side down, and it wiped all the resistive stuff right off. So I ended up with the most expensive blank PC board you ever saw. Took an entire electronics class doing it, sitting there agitating it with the ferric chloride.
Yeah, stained my parents' concrete.
I stained mine too.
I was rummaging. Just yesterday, I was rummaging, or last night, through the remains of what was in my garden shed, which I had originally set up as my workshop and electronics area, but it was too small and not sealed or air conditioned, so it was very, very dusty. And I realized I had
Go ahead.
I found, I don't know where it is. It's in my car still. I haven't brought it up to the office yet. I found this stuff that I used to buy from J-Car Electronics in Sydney. My favorite store in all of Sydney is probably to this day J-Car. If I go back and visit Australia and visit family, I'll find a J-Car store. There's a few of them now, and go there and just to hang out because it's my favorite place. But JK used to sell this stuff called press and peel. So people started getting laser printers and printing your PCB pattern mirrored on this laser printer opaque film,
and then iron it or something.
Expensive. And you would use that with an exposure box to make a negative, and then you'd use the negative with wrist-on to expose the pre-clad PCB. Then you'd rinse it or develop it, rinse it, then put it in an etching bath. It was a rigmarole. It took so long. It was only good for, at the finest, I'd say 20 to 25 mil trace and space. So for the analog prototype and basic digital boards I was doing in the 90s, it was okay, but you'd never do 6 and 6 or 10 and 10. And people started realizing you could ion transfer the toner from the laser printer, because it's pressed basically with an iron. You can iron it off this film onto the board directly, and then just etch the board and save a few steps. So I started doing that. And then they came out with a special product just for it that was designed to separate really neatly and give you nice straight lines and things, because people were doing it with paper and trying to wash the paper off. I still see that. I tried that. Still a lot of people doing that. None of those things work really well. I'd much rather just order boards from Oshpark, and then I can go down to 4 mil trace and space, and everything looks and I can use a 4-layer board with planes and have, good high speed signal. And it's hardly worth making your own boards anymore. It's fun to do once or twice, but yeah, I got rid of my etching tank and ferric chloride years ago.
Right. What do you think about milling the milling the boards and these other ways people are doing the?
I have a.
You have one, right?
Bils desktop PCB mill, not the current generation, which is they made the machine slightly larger and turned it into a generic mill that does both. That's really targeted at boards and any kind of mechanical subtractive manufacturing prototyping. And it's an excellent machine. It is excellent. I have the older one, which is still really excellent. It's limited. I can only really do 2-layer boards, and it's limited into area that I could do about this big, and it's very slow. Milling a board is painfully slow. But what makes it really nice is the software. The CAM software, you bring in your Gerbers or Eagle files, and it just works. And they did a lot of work on the software and the CAM software that comes with it to make the milling process faster and still accurate. And so it's faster than ordering boards in that you don't have to wait for them to manufacture it and ship it from the panel.
Right. But barely.
But it will take, you'll have to set it up and let it go, and it could take a few hours to mill a double-sided board.
Right.
Which is not bad, but you need other stuff to go with it. You need, like I got the vacuum attachment, and I need a dust extractor, and you need to take care of the machine. Like I'd noticed that with mine, some of the drives had started to seize up here and there, and I need to figure out what's the best way of maintaining it to keep them going. But I use it for prototyping RF boards because I can control the depth of the cut, and with the dust extractor I can cut FR4. That normally you shouldn't mill FR4. You should mill FR1, which is paper phenolic.
Right.
Paper phenolic is a high loss, high decay. It's not really. It's that material that you can heat it up and they stamp the boards, and it's used in mass-produced single-sided consumer products. It's that brown-colored PCB that's got that phenol smell to it, and if it's running with hot components, the heat actually over time causes it to start to char and become resistive. So its insulation capability drops over time if you're using it for, say, a Class A audio power amplifier, it's going to end up starting to become conductive over
it cooks.
lifespan. Yeah. But that stuff is perfect for really simple boards for mass-produced items because they heat it up to 140 degrees C and it's stamped. They don't mill it, they don't cut it, they run it through massive machines that just stamp the boards out because it goes real soft, like soap, or cheese.
Right.
So that's
yeah,
phenolic, but that's FR1. FR1, the first grade of flame retardant materials, paper phenolic, and milling that, you don't get glass in the air. So it's much safer, and you're not going to breathe in glass dust, which you don't want to do, right? So the mill's cool, but it's very limited. But I can use it for some basic RF prototyping because it's fairly accurate, and I can make stubs and antennas and stuff using it. But it takes a long time to cut away all the material.
Right.
Yeah.
Now, have you used the technique when RF prototyping where you actually do strip lines where you cut another piece of a PCB and actually just mount it above a ground plane PCB?
I have not. I know that's popular, and a lot of radio hams do it that way. It's like dead bug is what we call it, because you can actually take some of the RF transistors and
squash them out to, Alan Wolke does that.
Upside down onto, like you start with a blank bit of pre-clad copper, you polish it, you spray it with lacquer so it doesn't corrode, and then you can glue your parts on top of that and wire them over it so they have a ground plane.
Right.
Trying to call me.
So, yeah, now when I prototyped, I made a couple PCBs when I was young, but I used, I went back to regular old perf board, right?
All right.
And my technique was go to Radio Shack. Go to.
And believe it or not, all the holes in the board itself are punched. They're not drilled.
You could see it. You could see it when you look real close.
Yep.
All right, so I used to use PC board like this.
Yeah.
That's what is that? Where's my glasses? Wow, I've lost my glass. Okay, here we go. Don't get old, people. You can't.
Now that one looks like it's actual fiberglass, though. That one.
Yeah, I believe that's actual fiberglass. Yeah.
Yeah, Twin Industries. I used to buy their stuff from Fry's. Twin Industries had boards like that, but they had plated through holes and top and bottom ground planes around all the holes as well. So you can see some
and stuff like this. Yeah.
Those were really useful, but in the end, I got so jack of how long. Like, think about how long it takes you to build a prototype of something using that stuff with all the wires you have to solder in and jumper everywhere. It's really not worth the time anymore. Just design the board and go to Osh Park. Design the board, go to PCB Way. Design the board, go to JLC PCB. Design the board, go to Next PCB. Design the board, go to PCB Cart. Whoever it is, be willing to wait a few weeks. Your time is not worth how long it takes to use all that jumper wire and solder everything manually, unless you really cannot wait 2 weeks. If you have to have something within the next few days for a project deadline, I get it. And I actually have a suggestion. I found this really cool, weird software written by some guy in Melbourne, Australia, I think, that'll take a net list from OrCAD or Protel or some old format that you can still generate from many different ECAD tools, and it'll put it into a proto board CAD tool that lets you figure out where to place the parts and which traces to cut. Proto boards, we call it Vero board in Australia because, that stuff. And it's a CAD program for helping you figure out where the cuts need to be and where to lay everything out.
Now look at this. This is one of my great examples of what not to do. Can you see what's wrong with that board?
They've got power and ground, but they've shorted them at the end.
They're interdigitated. Power comes from one side, ground comes from the other, which means the inductive loop is... Oh, it's horrible.
That's
it's
how
just,
people were taught to do power and ground in 1985.
Right.
Because all
it's
the
just horrible.
series logic had VCC at the top right and GND at the bottom left, and you would run power and ground on your bottom layer or top layer,
right,
and have all your decoupling caps, and then the bottom layer you could have all your memory routing, tons of horizontal traces parallel.
right, right,
terrible for modern parts, and EMI goes through the roof.
Right. Now, we didn't talk about for breadboarding. I've never used really the breadboards that people really like these days. Well, I shouldn't say these days. We had them in the old days. I like the little ones. Sometimes I'll use like a 2x3 inch. You'll see on my Hackaday videos. You'll see me just do like a chip or something, and I use it as a breakout board, really. But the contacts and all that metal that's underneath, think about that on I don't have on the boards handy, but think of all that extra metal underneath a breadboard, the plug-in breadboards, all that extra metal is hanging off of each single trace that you touch. It's just antennas, inductance, all kinds of stuff. But it's got its place, If you're lighting LEDs, it's perfectly fine. So, hey, I have some good news, some big news. So, we did a show a couple weeks ago on the Commodore 64 schematic, and we talked about it, and we looked at it. We said, look, you can tell they must have had artifacting moire patterns because they phase locked the dot clock to the color burst and stuff. And since then, I've been in touch with Albert Charpentier, the designer of the VIC-1 and the VIC-2 chip, and designer of the VIC-20 and C64, as it turns out. Him and Bob Yanis did the first one. So I got a history lesson. So Albert has agreed to join us 2 weeks from now on Friday. So we're going to advertise the heck out of this.
Spread the word. The VIC chip legend will be on the Coriolis effect.
And nowhere else. He's been out of touch all these years until he showed up for World Computer Day. And me and him spent the whole time gabbing, it seemed like, on the World Computer Day thing. We gabbed for an hour that day and a couple hours since. So, this will be your chance to ask any question about the genesis of the C64 or the VIC-20 or the chips that are in there. And I'm sure we'll have a bunch of stories, too.
I just want to share this real quick because I couldn't remember the name of this app, but I'm going to show it.
Okay, very good.
It's called VCAD. Now you're getting my...
Okay, so I'll find your
I did a screen
share. Yep. Hang on a second.
I don't know.
And your screen share is blue.
Okay. Let me try this again. Switch screen or window.
And I got the normal echo out of it. Somebody asked about the Rev 1 VIC chip 20's voltage regulator. That'll be a great topic because, in theory, I know some of the story behind that, and I wonder if my version of the story is correct. Because I know somebody that took credit for melting the plastic on a VIC-1 plastic case. Bob Russell literally said, that was me, that's my fault. But Bob's a programmer. So first off, he'd be excused for not knowing the thermal equations. But second, why is the programmer in there doing the voltage regulator? So I have questions too.
That's really bizarre, isn't it?
Yeah. All right, so I see your screen. I'm going to make it real big.
I don't have a really fancy, elaborate design to open in this, so I haven't done one recently. I wonder if... Oh, look, there are a few other ones here. Let's do this one. Water alarm Aterado. This might be a... So this one uses some different types. There's different types of proto board you can load into it. So this one has one with these different weird patterns. But it just shows you where to put the jumpers and the components.
Whoops. Yeah, my bad.
It's all right.
Okay, go ahead.
So it just shows you where to put the jumpers and components and where to cut traces.
Hey,
after loading in a net list.
Okay.
There's a library as well, like you can. I don't know what this does. Oh, this put the whole library of the design into this thing. So I've got to separate these parts out. But you can, it's really funny. It's a PCB design tool for protoboarding. So it's actually super useful for one-off guitar pedals and stuff like that. Why am I getting that error message? No, I don't want to save. Let's try a different one. What's serial in-system programmer? This charger 1.2 amp hour. What's this board? Oh, this is a more complex design. So you can see this is typical Vero board, just with traces going in one direction only. 0.1 inch spacing. There's some big power resistors in here. So you can add to the library, and it's basically an outline of a part, and it's pins, and which is pin 1, which isn't. You can see the ICs are in here, and all the X's are cuts, and then all the rest are jumpers. So this can save you. So you do this and then print it out on a big sheet of paper, like tabloid, 11 by 17 or A3. Print it out real big and print it out 1-to-1, so you can compare your actual proto board with the design according to the net list. But again, like you're not going to do anything USB or high speed or this
right.
This is only good for DC, which is audio frequencies and lower, basically, for proto boards these days. But yeah, it's pretty cool little tool written by a fellow Aussie. It does cost money. I did buy a license. I wanted to support him, but it's really, really cheap. Roger Lascelles.
What language do you reckon that's written in? What?
Probably Visual Basic, I'd guess.
Yeah, that makes sense.
A lot of tools like this that I've found over the years were done by engineers who just quickly wanted to throw something together for themselves and then realized they had a product they could sell. Visual Basic. Yeah, I'm checking for updates. I wonder if he's he's made it free and open source. How about that?
Well, give us the web address again then.
At vcad.com.
Oh wow, great name. Great.
Download the latest VCAD. Look at this. And it works on Linux and FreeBSD and OS X as well. Oh, that's awesome. It's cross-platform. Now I'm going to download the latest version and see what source it is. I'm going off on a rabbit hole here, but
yeah, not a problem.
Look at that, Object Pascal. How about that?
Wow.
Maybe someone who used to work for Altium, because Altium and Protel back in the day was all written in Delphi.
Okay. Yeah. Hey,
No,
so Wes asked if you've done any pedals yourself.
Oh, many. Yes.
So
and
Wes
we talked about them in prior episodes, but Wes missed those. The most recent ones, of course, I did in Fusion 360, which is actually the ideal CAD tool for designing guitar pedals. And
because of the physical interface,
yes,
I assume.
Many of the guitar pedal designers, boutique pedal companies here in the United States and around the world they were using Eagle for their boards, but they're migrating to Fusion because it's the same files and it's basically Eagle, but you have it fully integrated to the mechanical layout. So it makes it so much easier for doing your drawings of where you need to drill out all the holes of your box and stuff like that. There's no better tool for guitar pedals, in my opinion, because the pedal itself is simple enough. If I had to do a hairy digital pedal with some FPGA or DSP processor and VGA packages and lots of memory chips, that would be different. I'd use Altium for that for sure, because just as a PCB tool, Altium is built for it's got the horsepower to cater to more complex design.
It's more mature, right?
Yeah.
Also Altium? Yeah.
Oh yeah.
Yeah,
Well,
so
no. Yes and no. Yes and no. Fusion as a PCB tool is not mature. It's only been out for since the beginning of 2020, so 2 years. Uh,
right.
but the engine is Eagle, which has been around, perhaps even
Oh, that's right.
longer than
Yeah,
that.
I'd forgotten about that. Yeah,
Yeah.
yeah.
But
Hey, so go back on your camera,
Oh, I'm sorry.
unless you're done here.
Yeah, I'll stop with the rabbit hole going down to VCAD and all that. But
Well,
that's something cool.
yeah, while you were talking, somebody just talked about a great reason to come to VCF this year. Oh, your screen share is still live. That's very cool.
Well,
Hang on a second.
I've noticed your XSplit. This is a clever thing with XSplit. It retains the screen share as a static image after.
It does. Yeah, yeah. So I can pull that back.
Yeah.
But somebody was reminiscing about 4 years ago. It was the A4000. Somebody was doing the A4000 repair, and who meditation. The guys, Bill and Anthony, I think. Yeah, those guys.
Yeah.
And somebody was talking about a capacitor being installed backwards on the A4000.
Oh,
and
yeah.
I leave the room and I come back in and I've got Greg Berlin with me, designer, who's supposedly going to be at this April 22nd, April 23rd, mark your calendars, this VCF. And I did the typical Woody Allen. I'm like, I have here with me Greg Berlin, designer of the A4000. What were you saying about that capacitor? and it was really fun. They're like looking, and the guy afterwards, he said, I should have known not to bring that up in front of you, that you'd have like the designer with you or something like that. So we had great fun that day at the old at VCF. So again, I recommend that heavily.
Nice.
So, hey, I have a material selector from the DFM, and we're not promoting Audium here. I just happened to pull up their DFM sheet. I hadn't seen it before, and I said, hey, Ben, you mind if we look at this? Now that, we can look at anybody.
Yeah.
And so here's as you can see, better thermal performance than FR4 is how it starts. Yeah, do you want to kind of lead through? For example, it says greater than 200 TG. What's TG?
That's glass transition temperature. And I actually found an error in a dialog in the current version of KiCad, and I submitted a ticket, and they're actually the developers got on there and they're going to update it with the next.
Wow.
But because they were saying lost TG, but that's what's the word? Conflating two different terms. One is lost tangent, and TG is
right.
Glass transition temperature.
Transition temperature. Yeah.
So TG is a critical figure of merit in every PCB material manufacturer data sheet. You'll see a standard set of parameters, which are standardized now by IPC in the 4100 series standards, IPC 4100 series, and they have these what they call slash sheets. But each material conforms to that's standardized conforms to a slash sheet, which gives parameters for TG, TD,
right,
coefficient of thermal expansion, and they'll often give, good manufacturers will give you this stuff in a graph. So they'll give you a graph of temperature versus coefficient of thermal expansion. And the glass transition temperature, I wonder, Bill, if you could bring up a material data sheet to show so we can talk about this.
All right, I'll try to. For which product do you think?
Go to iSolar and download the PDF for FR408, because FR408 is the most...
Yes. I have that on my drive too.
It's kind of an industry standard material that's really good, that's high quality, low loss, but still very affordable. And it's the material that Oshpark and many of our low-cost prototype services standardize on. So,
well, and I was trying to get PCB Way. I was talking with the gentleman there. I was trying to get them to use it, and they did adopt it. Yeah, Anson.
We should get Anson on this show. We need
to
get Anson to join us for a stream one of these days. I was chatting with him on Facebook just last night. So.
Oh, okay.
Anyway.
Yeah, I'll have to give him a shout.
Yeah. And again, we don't work for PCBWay or particularly promote them. I do help with their yearly competition as a quote-unquote judge for some of the designs. But I just love what they do in the community they've built. And JLC PCB, similar kind of deal, you know. I'm just really happy we have these services that have a standardized product that if you're willing to conform to their standard, you can get something done really fast, really cheap. So yeah, there it is. So Isola FR408HR. This is the newer version of it. It used to be just 408. Now it's 408HR. Look at this. Look at this. 230 degrees TG. That's incredible. I don't know how they did it. But what that means is most typical FR4s have a glass transition temperature of about 130 to 140 degrees Celsius. Right? This one has, I guess, 230 DMA TG, but the basic TG is 190, which is much higher than regular. Why is this important? It's important. We'll come to that. TG is the glass transition temperature. It's where the material, the resin, the network resin that keeps it all together, starts to become soft and expands. Its coefficient of expansion goes way up at the glass transition temperature. TD is the decomposition temperature. It's where the epoxy decomposes and starts to delaminate and turn into a mush. Basically, it's the melting temperature.
It's right.
Liquid and gets horrible. DKDF. So you see, these are the main figures of merit. And that's why they're a subheading to the whole data sheet at the top in that red block.
Right.
TG 190, TD 360, DK, that's your dielectric constant, also known as epsilon sub R, 3.68. DF is dissipation factor, and that's your loss. It's also called loss tangent or tan delta.
Right.
They're the same parameter, but the industry,
it's like friction for electric waves. Yeah.
So if you scroll down, there should be some graphs. There's more data on the data sheet there. There's no
this appears to be a short one. It's only got a couple pages.
Okay.
I can find along.
They do provide it in the table, though. If you look at z-axis coefficient of thermal expansion, before TG, it's at the top of the typical values table, the fourth cell down, z-axis CTE or z-axis CTE. So A, pre-glass transition temperature. So before the TG temperature, it's 55, the slope is 55 parts per million per degree Celsius. So as you increase in temperature, the z-axis of whatever the material thickness is, it increases by 55 parts per million up to glass transition temperature. At the glass transition temperature of 190 or between 190 and 230, whatever it was on the top of the sheet.
Right.
Post TG, it's suddenly the z-axis expansion ticks up and it's 230 parts per million per degree C. So how we make boards is we etch them. We start with a core, a thin core that has pre-clad copper on both sides, copper foil. It's exposed, it's etched. Even before etching, it's drilled, it's plated through, then it's exposed to it's laminated with photosensitive material. All of that's shown in the document you had up from the Altium website, I believe. So we can walk through that. Then it's exposed through the mask pattern. It's developed and etched, and then that core with 2 layers. If you have a 4-layer board, then they put pre-preg, which is partially cured material of the same material that's not got copper on it. It's just the material, partially cured, is laminated onto that. Let's say you're doing a 4-layer board. That's put in a lamination press with copper foil added to it for the outer layers at high heat and temperature for, say, 4 hours in a lamination press. So during that time, they actually deliberately exceed TG to get the uncured prepregs to cure, and what happens is they get thinner because the epoxy, as it heats up, it turns to liquid and it gets pressed out, and they press it with so many layers of prepreg according to what you ask them for a final thickness. And part of the printed circuit board manufacturer's secret sauce is they know for all the materials they have on hand, or the material you're sending to them, they know exactly if you are asking for a prepreg layer that's 6.3 mils thick, they know exactly how much prepreg sheets of 2 mils stock to use and for how long and for what pressure to press them to get them to finish at the thickness you've asked for. And there's going to be some tolerance, right? But in that whole process, obviously, you've already etched and you've drilled through you've plated through copper holes for vias and stuff. All that stuff's moving around during the press. So the more layers you add in a build-up, the more difficult it is for very fine, small vias to be, and things like that, to be fully aligned properly and not be cracking up the copper. Generally, lamination, though, they've got it dialed in, and it's usually, if you just stick with what the manufacturer suggests or what their standard stack-ups are on their website, you'll probably never have a problem. So that's how that works. So that's why TG and TD are very important. But also, after that, you've got to put these through assembly where they go through a reflow oven. Now, for soldering lead-free solder, that whole board's going to sit in 250, 260, 280 degrees Celsius for maybe a minute or so, or even longer, maybe several minutes, depending on the reflow, depending on the solder you're using, and depending on the manufacturer who's doing the assembly. It's got to go through reflow. Now, if you're doing top and bottom components, it has to go through reflow twice. If you're doing reflow, plus you also have some through-hole parts that have to be selectively soldered or wave soldered. It's going through reflow maybe twice, and then through selective soldering in some areas of the board. And so the board is subject to like tremendous temperature cycling that's ridiculous during the assembly process. And that's not even to mention temperature cycling in its final use. So TG is a big deal. If you aren't aware of the expansion on your Z-axis during reflow, I had this customer who worked for a startup years ago who I was supporting when I was at Altium, and he was such a nice guy and a brilliant PCB designer. Worked for a startup company in Colorado. They were working on military-grade supercomputer, a military-grade supercomputer, and I'm talking in the mid-2000s. And it was kind of a roll of the dice because they were using these huge Broadcom VGAs that were very dense and having multiples of them to make a multiprocessor board that would go into a VME backplane. It was designed to go on VME. They needed to do a 22-layer board. So the board thickness was really thick. And they were working with a manufacturer that was this board house, I forget who it was, and I shouldn't say it anyway, just to protect the innocent. The board house in LA was a Los Angeles area board fab. Oh yeah, we can make this for you. We'll work with you. You know, you can have these plain layers. You can have this thickness copper. This is the material we recommend. Use FR408. But first they were going to use some other material by Rogers or something for some layers, because this was real cutting edge stuff. You know, they were doing multi-gigabit buses, which was cutting edge at the time. So they had to length tune everything. They had to have impedance control. And because of these very dense BGAs, they had to have they had a real struggle breaking out the BGAs on the board with massive via fields, right? And so they were doing some blind and buried, 2 layers of blind and buried vias and via stacking in the inner layers of the board. And the whole thing, they made the first prototype at the board fab, and the board fab's like, yeah, we did it. It was a $20 or $30 or $40,000 PCB for the first one.
Right.
It took up a whole panel. They did all the open short testing on it. They did the impedance testing and TDR on the test coupon from the side. Everything checked out. Like, great, we're done. We've done our prototype board. It works. It passes all the tests. Now, let's get all these another $20,000 worth of prototype, really expensive semiconductors, ASICs from Broadcom, and all the supporting electronics, the power supplies and everything, the memory, and they put it through assembly, and it didn't work. And they could, no matter what they did, they could not get it to work. So they did an in-circuit open short test again and found that all the via barrels were cracking.
Wow.
Because the board was expanding too much during reflow.
Wow.
And the thicker the board and the more copper is in the board, the longer it takes in reflow. So it's a compounded problem because you have more board, more thermal mass, more copper in the board. It has to stay in the reflow oven much longer because the whole thing has to heat up. And what does that mean? That means your outer layers of the board are exposed to the highest temperatures for a long time, and the inner layers take a long time to get hot. So the outer layers, your blind and buried vias start to crack. And so, so how do you fix that? You do what you can to reduce the number of layers, yes, but you also have to start doing other exotic things, like you have to limit the minimum size of your vias. You can't go down to 2 mils or 4 mils. You're going to have to figure out how to have bigger vias. And then you're going to have to fill the vias with copper. You're going to have them plated so that they're full. So the via is like a big chunk of metal there's not a hole in the middle of it. So
right.
Yeah, it's not easy doing big complex server or supercomputer boards. And unfortunately for my friend who designed the board, he did his job great. But the company had no more capital left after that to pay for a second run. So they just shut it down. The investors pulled out.
Wow.
And they went nowhere. They had to close their doors.
So I pulled up PCBWay's page here, and you can see the material selection actually allows you to select by TG.
Yeah, that's right. So you can get 150 to 160 or 170 to 180, which would be the FR408, and they'll just charge you a little more for it because the material costs them a little bit more,
Right.
But no problem.
Now,
if you know you're going to have components mounted top and bottom, so that's 2 reflow cycles, and if you know your board's likely to be used in a harsh environment, you should just spend the money and get the better material.
Right. So yeah. Well, very cool story on the barrel. How thick was that 22-layer board at the end of the day?
It was, I want to say, a quarter inch. No, it wasn't a quarter inch. It was about 2/10 of an inch thick.
Right.
So, and that was another problem. They built the board and then realized it wouldn't fit in the card slots.
Right.
In the VME backplane. And luckily, my friend who designed it had enough of a pullback on the planes and surface layer routing from the edges of the board. He didn't go right to the edge with traces. He was smart and it made a clearance. And this is a DFM topic. You've got to decide based on your application, how close to the edge can your traces and copper go in plane layers.
Right.
Fortunately, he had designed it so he had about 1/4 of an inch clearance on the surface layers, and they were able to
Mill it down.
mill it down just on the edges so it could fit in the card slot.
Wow.
But
I
still,
haven't seen that one.
it didn't save the project. They still had the one thing that killed the whole company. Game over. People lost their jobs, right? Everyone. Investment money gone. Via barrels cracking because of glass transition temperature and the coefficient of thermal expansion not being correctly taken into consideration for the whole manufacturing process. Not just board fabrication and lamination, but assembly as well.
Right, and that's not even use. That's not even in use inside a computer or whatever. It never left the factory before it cracked its barrels.
It was DOA. Yeah, that was a stillborn child, and there are very few things more heartbreaking.
Right. So,
but these guides are pretty good, and a company website like Altium knows that content like this is valuable and it brings eyeballs, and that's why they do it, right? It's content marketing. Sierra Circuits has some amazing, excellent content on this.
I tried to find Sierra Circuits' DFM before I found the Altium one. But I didn't find it. But you and me have talked about that in the past, and that is a great guide.
They have a series of PDF guidebooks that you can download that are exceptionally good, that are well written by people who really are experts. You just have to be willing to sign up for their marketing emails to get them.
Right.
And once you've done that, you can unsubscribe. But Sierra, like, honestly, I know the guy that drove that there. I met. He's kind of the son of the founder, and he's a marketing and sales genius, which is why they did it. But actually, they built a business too where they really get this and know that people need to learn this stuff, because it costs you money if you don't know this stuff. It causes scrap and pain. And worst case scenario, loss of work, loss of income. So, yeah. So, I like this though. I like how the low-cost prototyping houses have all got standardized options, and if you stick within these, you're gonna be fine.
So I went to
Seed Studio was another one. Seed Studio had their Fusion service, Seed Fusion, and they have. You can download. I don't know if you can download it from PCBWay or JLC PCB. But some of them give you downloads. In Europe, there's Euro circuits. They're also really amazing. Dirk Stans is a great guy, and he's done a lot of work to make it easy for people to not have these problems by providing design rule files that meet their manufacturing requirements and avoid these issues.
Right.
And you download them, put them in your CAD, and you're pretty much good to go.
So I tried to go to JLC PCB, and I did not find the option for FR408 anymore. I didn't find the impedance control at all. So I'll tell everybody in the chat, if somebody wants to go to maybe it's something from the pandemic or so, or from the
they may have
not pandemic.
Maybe a supply chain problem.
That's what I was trying to say. Yeah.
They have equivalent materials that are manufactured by other manufacturers though in China as well,
right?
And they're
yes, they do.
Yeah. So
and they're even labeled 408 is what I've seen.
Yeah, you just have to be willing to read some data sheets and figure out, like, is this actually equivalent? Or you can go to a fab and specify by an IPC slash sheet. I mentioned earlier in the call the IPC 4100 series standards. And yes, unfortunately, they cost a lot of money to buy. But if you're working for a company doing boards, the company should be an IPC member and should be able to buy or download the standard. But you can use the slash sheets and specify your material by slash sheet. So you can say, I don't care what material you use, just make it comply to slash 66. IPC 100 slash 66.
Right.
This thickness. Dielectric constant within this range, etc. It's all there.
Right, and you can see when I select 2-layer boards, that the default is one version of TG. What is that? TG 140. But when I select 4-layer boards, and I'm under the advanced section on PCBWay now, it automatically jumps up to TG 150.
Right. Yep, because they're using an equivalent to FR408 anyway. Hi, Amazon's here. That's always a happy moment.
Very cool.
Thank you, sir.
Very cool.
You have a great day. This could be an unboxing episode too, Bill. What did I get? It's heavy. I like the weight of this.
Maybe it's PC boards.
Might be a book. Everyone want to see what I got here? I think it's a book.
Oh, I want to see your PCB book then when you're done.
Oh, wait. No, it's not a book. I know what it is. I did want these. I've got a packet of XLR connectors because I'm making some microphone cables later today to sort out the studio side of the office.
Yeah, well, I've got a nice selection of Medusas here. I just used to love those things, so I do everything with those XLR bundles, of 6 or 12 or 24.
Those are good. Yeah. And what's this one? Oh, it's a replacement laptop power supply. Nothing that fancy. Just a generic power supply. So I can have one at home and leave one at the office. Anyway. All right.
So let's let me see if I bring this one to the front.
Blog site. What are we looking at there? So we talked about TG and why that's important.
Right. Hang on, I got to find the right screen. So what's next in our material property selection?
Dielectric constant, that's obviously critical. Current carrying of copper.
I was jumping down to that. That's a cool little section.
Okay, those graphs are copied directly, lifted straight from, screenshotted from, and reused from, probably without permission. IPCA, you're paying attention. This is IPC copyright material. I've seen those graphs in so many places. I think that's
right. It'd be easy to generate them with some Excel.
Yeah, those are. Go back up. Why do you keep scrolling away from them?
No, I'm sorry. I'm looking to see what's next. I thought there was more here. Go ahead.
This is current handling capacity of a PCB trace by cross-sectional area. That's not a one-size-fits-all. This is very misleading, and this is why you have to be extremely careful if you get information from somebody's blog because you didn't buy the standard. If you look at IPC 2152, is it 2152? I think 2152 is the current carrying capacity standard. It has dozens of these graphs in it.
Right.
And you have to pay attention. What does that say at the title of that? It's 2-ounce internal vacuum poly. What does that mean? This is a 2-ounce layer of copper, internal layer inside the board. The board's in a vacuum, and poly I forgot. But basically, there's different cross-sectional areas and then different currents, and that's not what you're allowed to do. That's just for each of those curves represents a temperature rise in a trace that's longer than an inch. If you have a tiny little trace that's next to two big planes joining them, like we used to have an A ground and D ground, which is not fashionable anymore for many reasons. That's another whole episode. If you have an A ground and a D ground and a little bit of trace joining them at a Kelvin point, then in theory, that Kelvin point has basically zero current flowing through it anyway, if you've done it right. But no one ever does it right. So there's current flowing through it. But there's heat sinking on both sides of that. You've got massive copper planes sucking heat out. So this graph does not apply in that situation. This graph is empirical data gathered from experiments with sections of printed circuit board samples and traces of a uniform width just going across the circuit board and placed inside a vacuum in a chamber and then temperature sensors on it, and then current put through it to measure the temperature rise. That's all this is. That's what
Right.
this is. But how to use it? How do you use this data? Well, what you say is, if I know I'm going to be having a maximum of 10 amps DC through this trace, how thick do I need to make the trace? Well, it's a 2-ounce copper. It's an internal layer. Okay, so I look at the 10 amp line, and you move across, and I go, I want to say a 20 degrees Celsius temperature rise in the trace is acceptable.
Right.
Because my operating temperature, maximum T ambient specified for my design is 40 degrees C. The trace can go up to 60, that's okay. So you follow the 10 amp line, you go across to where you see the curve of 20 degrees temperature rise meets the 10 amp line, and it says, well, your minimum cross-sectional area for the trace needs to be 0.4 square millimeters in that case. So you take that to the graph below it. So scroll down a little there, Bill.
Yep.
Take that to the graph below, and you go, okay, what's a 0.4 millimeter cross-sectional area trace on this graph? Cross-sectional area. And they're actually missing the y-axis labels. So I can't even tell.
Yeah, they are. Yeah.
But you go to...
So there was a formula here. That's why I was scrolling down earlier, is they had the plain old formula. Oh, there it is. The R equals
that's
PLA.
Yeah, that's resistance.
Yeah.
And that's not the whole picture either. You need to cover that. The truth of this whole thing is actually you have a three-dimensional object of an obscure shape, which is PCB materials and traces, and you need to actually do a finite element analysis to do a proper thermal simulation. And that's where simulation tools come in, like COMSOL or CST or ANSYS IcePack, and they actually take the whole board structure with all your copper, and they say, well, if you've got an amp coming out of this regulator here and sinking into this chip over here, this whole thing's actually going to have that much temperature rise just at that point.
Right.
You know, it
right.
First of all simulates the current density in the whole circuit, element by element, voxel by voxel. And based on the current density, then it uses that resistivity and joule heating. It's called a joule heating problem. They use Joule's formula to convert the power lost in the copper to joules,
Okay.
which is translated to heat in each voxel in the three-dimensional shape. And then that's what those tools do. And it's very complicated numerical methods that take a lot of computing power, and software is expensive. Unless you
I was going to ask if there's affordable software or any cheaper approximation software for this stuff.
There are tools you can use for free. There's always a free alternative, and they're usually harder to use, much harder.
Right. Right.
Or not as good, or specific to one situation but not to another, and you would have to modify the source code. I'll give you some hints, so if you want something free, ANSYS does. I just found out ANSYS does have a student version, so that's one thing. If you're a student, have a student version, which is cool, and it's quite capable. I believe COMSOL also does, but it's been a while since I looked at COMSOL. There's finite element method magnetic, which was designed to simulate magnetic devices and coils and transformers and motors. And it was written by my friend Chris Carlson, who used to work at EMOLS. Worked with a guy named David Meeker, who was an electromagnetics absolute guru. He's a consultant, and he wrote his own software and made it free. I think it's open source, but I'm not sure. It might just be freeware. But it's called Finite Element Method Magnetic, FEMM, and it not only will simulate magnetics, but he has a tutorial that shows how you can also use it to simulate, do basic thermal simulation, like heat transfer simulation.
Right.
And it's a really good, well-written, quality piece of software, even though it's free.
Right.
And it works with GNU Octave as well, so you can automate things through Octave.
Right.
Then there's Octave toolboxes that'll do it, but you have to be willing to write code. That's the problem.
Right. So, hey, show us your PC board handbook. We're up the top of the hour. Let's.
Sorry, I've been yakking and yakking.
No, this is the science of what people don't know about when we talk about things like PC boards.
They're talking DFM. We only talked about CTE so far, and
that's it. We talked about TG and yeah, that's and then this, yeah.
If you really want to learn DFM, this is what you're looking at. This is a collection of scientific papers from the industry over many years, edited by Clyde Coombs and Happy Holden, who's kind of known as a PCB guru. This is 1,600 pages, and it's kind of expensive, but it's a worthwhile investment.
I'm looking to see what year mine is. Hang on a second.
You've got the 3rd edition?
Mine's from 1988.
And I have... This is the 7th, which was the last one before Clyde Coombs passed away. I think they were talking about working on an 8th. Somewhere I had a copy of the 6th too. I think I gave that away or left it at Altium when I left there. But the 7th edition, I think, is the latest published edition.
Mine doesn't have page numbers. It's got section numbers, like 11.5.
Wow.
Let's see if I can show some of the cool stuff that's in here. I doubt it. Ooh.
This is a passion project. The people who put this together did it because they love the industry and are all about PCBs. It's rare that something like this would be put together otherwise, you know.
So yeah, I just happened to turn to a page. It shows chip carriers. It shows wire wrap, flat.
Cool. Look at that! I had an 80C 188 in that package. It's ceramic. That's a ceramic chip carrier for a zero insertion force socket.
Right.
I happened to have an 80C 188 in that package. Again, it was one of the chips I inherited from a guy when I was a kid getting into electronics, and I ended up selling it on eBay quite a few years ago, and like it sold for good money. People wanted it.
Right. Now, the one you're talking about, that's the 8-bit version of the ADC 186, right?
That's right.
Yeah, I've used that. That's a nice.
The 186 and 188 never made it into consumer computers. They were only ever sort of used in industrial systems for some reason.
And that's what I used them for, was controllers. Yeah.
Yeah, people went straight from the 8088 and 8088 to the 80286. You know, the PC to the XT to the AT.
So, Mike, you're going to have to get yourself one of these books.
I never saw an 8086 in any consumer computers either, even though it would have made sense. Like, wait, this is the 16-bit external bus version. Why wouldn't you have 16 bits?
I looked at it as a step up from the 8051. That's kind of how I treat it, except that it had the weight logic built into it. That part I liked. You could interface DRAMs to it real easy.
The ultimate upgrade to the 8051 was the, in my opinion, though I never professionally got to work with them other than demoing tasking software for Altium, was the 8051XA from Philips. They took the 8051 and said, let's just make the whole thing 16-bit. And
so Eli Hughes from our chat channel just mentioned they were able to get 20 layers on 62.5 mil stack up to fit in a standard VME card guide. They spent a long time on PCB fabs, selecting materials, etc. talking with them early is super important.
Yeah. I don't know how you pulled that off, Eli. A standard 1.6 millimeter board with 20 layers.
Yeah.
Hats off, man. That must have
So
been
somebody asked ISBN number. Here's my old one. Mine's again from 1988. I don't know if the ISBN number stays the same.
No, I'm sure it doesn't. Although, wait, show it up again. It's yours is 07 070122609. Yeah,
Yeah.
the ISBN is very different.
Yeah, show yours. Put yours right up to the camera.
Added digits to them.
Closer. Yeah. Okay.
It's not the same. But
Okay.
If you don't have, like, this is a reference. This is not a book you just go read through, right?
Yeah.
It's a reference. If you're about to do rigid flex for the first time ever, then you go to the section and just read the section on rigid flex. While you're setting up your design rules at the beginning of the design, according to your design specifications.
Right.
That's what you do.
Right.
It's a desktop reference. Well, it's a bookshelf reference.
Actually, Mike Fikes just went out and bought one. I knew he would.
Yeah.
And he posted one of the his numbers.
Another book which you should be able to pick up for free if you ever come to. You may actually be able to get sent a copy for free if you go to the right place. This used to be a For Dummies book, and you could get a free copy. I'm not sure now if you go to DesignCon or PCB West or any of those conferences where this author or the company he works for is, or that sponsored this book is likely to be, they'll probably give you a copy. It's called PCB PCB Basics for Buyers.
Right.
It used to be called PCB for Dummies.
Okay.
The first edition was a For Dummies, but the publisher, the author and publisher or sponsor wanted to disconnect from the For Dummies company, whatever that company is.
Sure.
Because they wanted too much money for it or something.
Hey, can you post that in the Discord? Where to find that during the week sometime?
I'll do it as soon as we stop transmitting.
Okay.
Stop streaming. But and again, this is an incentive. If you're finding this on YouTube, go to our Discord.
That's where I was headed.
There's a Discord link at the top. Join our Discord. I'll be posting some links to some of these. But the reason I promote this book, I ended up buying a massive box of these to give to the salespeople at Altium when I was still there, because it's like these guys barely know what a PCB is, and they're trying to sell PCB design software, and they don't understand all the power in setting up design rules and all of that. This book is the best, most succinct. Start from scratch. What even is a board? What goes into them? You know?
Okay.
With images. You could probably get this for free. I've just remembered, you can get this for free from a download link in PDF, and you'll get the images in color if you get the PDF copy. So just do that. I'll post the link to the PDF when I have a chance, and it talks about, you know, how components are attached and soldered, and what specifications and standards you should care about, how to design and define them.
Also available from Amazon for $6. Somebody just posted.
How to document layer stack ups for your fabricator so they get it right and build what you're actually intending. And what I really like is it walks through the entire lamination process in detail, step by step, and talks about what I mentioned earlier. You start with a core that's pre-laminated, and the core gets drilled, and then plating happens.
Okay.
Right, and then that gets laminated up with, you know, additional plating and layers. It goes into way more detail. It talks about how they actually use tin as an etch resistant in the factories. They don't use plastic. Like if you make your own prototype boards at home using ferric chloride or ammonium persulfate, you're essentially using some kind of plastic as an etch resistant, and the plastic coating on the traces from either your laser printer or some other developing method is what the acid can't eat through. In the factories, and this is way more accurate, and this is why they can go down to such fine traces and spaces, they use a different metal. They use tin.
Right.
And the acid won't etch the tin, but it will etch the copper. Isn't that interesting? And they recycle it all too. They recycle it. There are fabricators here in Southern California, the boutique ones that do military stuff.
Right.
That have pretty much zero exhaust. That all of the material is recycled. The stuff that comes out of there is actual circuit boards.
And it's illegal from what I understand, you're not allowed to have a PCB etching house in New Jersey. That the chemical rules, you can't do chrome plating, and you can't make PC boards in New Jersey due to our environmental laws here. I've heard. I don't know if that's true, but I've never seen a PCB
it wouldn't
fab
surprise
house
me
here.
It wouldn't surprise me, and I'd say I hope every state doesn't go that way, because then we'll have nowhere where it can be done except for China. And
We'll have no PCBs and no shiny cars. Yeah.
I got nothing against China having factories. There are many different possible opinions one might have on that. I think they're doing a lot to clean up their act with the environmental stuff, and that's good. There's still a lot of work to do that they need to do, but I think it's wrong for one country to say, "Oh, we're clean, so we don't do any of that." What does that mean? What does that really mean?
Right, because it's still then you're outsourcing to a country that's polluting.
Yeah, you've just given it over to someone else who doesn't give a damn.
Right,
Actually,
exactly.
You're harming the environment by doing that. You should be reshoring some of that and showing how to do it clean. That's what you're doing.
Right.
Teach the world
Hey, so
you know?
Last question of the night. Chris asked, is anyone doing direct silver photoresist?
Like silver ink? Or...
Yeah, I don't know. I haven't heard of it. I haven't heard of silver photoresist other than silver being in, the photography process.
I don't know about that either. We should perhaps research that and come back.
Well, let's call it a day here then, and there's some homework for the two of us. We'll post that book. By the way, other people said they bought the book. Somebody just said they bought the book on eBay now and stuff. So we should get sponsors, and help promote their stuff.
Yeah, we should.
So
actually, coming
excellent.
Up here, I need sponsors. I'm going to be doing more and more of this kind of thing, and trying to make it. I've got a short runway, but I'm going to do my darndest, because you know what? If Robert Faranek, and he's a friend of mine, he's a great guy. If Robert Faranek and Dave Jones can be content masters and make a living, so can I.
Right.
I mean, I did it for Altium for 16 years and made a lot of other people rich. Now it's my turn.
So, yep. And meanwhile, dare say that if somebody needs a layout expert or whatnot, you might be available to do some layout and any number of CAD tools, any number.
I am an expert at Altium, all things Altium, because I was there so long and was a product manager and so on. But I don't mind answering questions here and there from friends, but if I start getting inundated with technical support, I'm going to have to charge for it.
Right. Right. Yeah, there's a difference between free information and actual work. But I used to say information's free, but it's not really. It's there to show our level of expertise, but this stuff's hard, and yeah, it's a per hour business or per project business, depending on how you go.
Yeah. Actually, information wants to be free, and I think by and large it should be. I actually like the content creator model, although it has challenges and it takes time to build it up.
It's got a lot of challenges.
There's a lot
and
of
it could change at YouTube's whim. Yeah.
And YouTube, you're relying, unfortunately, then on, and then I could say, well, so I'm not making someone else rich. Well, I'm making
YouTube rich.
Google shareholders rich. But whatever.
Yeah, somebody just posted that. Can you make Electron Ash posted? Can you make me rich, please?
Yeah.
So, All right. Well, hey, good seeing everybody again today. Remember, 2 weeks from now, we'll have Al Charpentier on if everything goes well. I mean, stuff always could have a glitch, but that's our plan for now. Check out Coriolis-effect.com and
stay tuned and
see us and check out our Discord. And stay tuned. See us here next week.